Oh. And but he did what he wasn't because it was supposed to come back one of the next day. And he needed it. So now, 4 days after it happened, my mom almost got rich. Why don't you show me what you want? Companies that get government. Just pay my son. I turn on the screen. I know. No, real offense.
Great, I couldn't see it.
Where are you gonna get? Tomorrow morning. Thursday. Yeah. Do you like hearing? And we're hoping to get out more. Tomorrow, yeah, Thursday. Right. Yeah, I'm not gonna be a winner. Yeah. Snuggle out.
How you think, man?
Good. Yeah, French.
Not Friday to your Sunday. Not Friday to your
City. Yeah. Well, it was more of I think the motion.
Yeah, you're
Very.
great to be here.
Some,
David.
Oh.
This was, yeah, and
All the big house, and strategies.
that was my first. Thank you. That was for. Is that 80?
My girlfriend lived in Rock. Yeah, that's
Three.
it's like, well, there's community that actually.
So it started with my grandmother.
Yeah, yeah, hanging their boards or.
I've never seen it first time.
Yeah.
That blurry thing, you know? Some of them not that.
Now the whole and neighborhood.
Got to tell us what you
Fighting.
really
They don't talk about it. It's like.
You sort of please.
Yeah, and it.
That's good.
Yeah.
I think it's the chip.
It's a certain. Now I'm using a. Okay. I'm in the deep end. I went against it. I went against every.
Wow. Yeah. Our social. So we're thinking now. Once again, more. Because I am. I'm gonna get some. Very much. socializes about the social events, on the softball team, volleyball, additional. It's a small town. It's still. What is in the, yeah, really.
Wow.
You know, get enough energy for. How did I get that? We haven't lived this many years. Oh, that's true.
Okay, we're actually working.
But yeah, so.
First,
Okay,
I just, they were next door.
okay,
If they want.
sure,
Food.
absolutely. Some came last month.
I wasn't serious about bringing the pizza. Oh, I'm sure. they'll never say about it.
Yeah.
Free pizza. It's a
Okay,
beautiful thing.
hey Kathy, hey Kathy,
You got it.
So when did you guys? Something's wrong with the universe here.
The Wi-Fi.
you have to register. I can tell you how to do it. I can tell you how to do it. You have to. Select, we haven't had yet.
Yeah, yeah.
That'll come up.
Well, I'm around the. Yeah. I make all this email.
Yeah.
They did check that. That's cool.
Right. Yeah, all of it.
Ethics and stuff.
They used to be on your place.
Yeah.
But, you know, I'm trying to figure out how this makes sense. I knew it was so bright, like, so.
Yeah.
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 I mean, it was like-
Yeah. Instagram, I actually do. This is not conversations, it's constant. There's things about each of them. Yeah.
It's really an audience.
It's absolutely like suggestion. Yeah.
You only see. They got primary doctor.
Right.
Yeah. So excited. I looked at everything.
Oh, okay. Yes. Bitter beer. He does a lot. You would like us yeah. No, he's. Oh. Yeah, they're. Yeah.
Oh, I'm so. That's where. Same thing with academics. Where.
Take pictures.
Yeah.
Yeah, there's all the main, how many. Yeah. There. They have.
It's not a lot of.
So, and
I would occasionally get some.
Right.
I would have to call myself to say, like, I cannot go, like, speak for all the minutes.
Especially. if it's getting-
Finding out that it's like, yeah. Like, you're like, five.
We're gonna.
And last.
Switch to.
Right, those things are now. Now I've staff. And then like, for that.
Small area.
And then. Well, when is it?
We got using seven.
They bring them on that too.
But you're not. No, I'm focused. And this one. What, there's a lot. Yeah.
Right. Wow.
Hi, Janet.
Hi.
Wow.
Flies are the same.
But.
7:33. 7:32, sorry.
No, I knew that.
We're ready to go.
Yep, talk to them. I'll just keep it here.
Okay, guys, let's get started. We got a bunch of people out there in virtual land that are sitting there drumming their fingers on the desk and saying, hey, guys, get this meeting started, Hockenberry. Anyway, everybody who is here and everybody who is out in virtual land, welcome to the October meeting of the Chester County Astronomical Society. We're glad you are all here. To those who are here for the first time, a particularly warm welcome. We hope to see much more of you in the future.
We don't always get pizzas.
For those of us who were here last month and saw a fantastic presentation on the DART mission, what a success. What a success. They were hoping to slow that period down by a few seconds, 10 seconds, and they got a heck of a lot more than that. Boy, was that a success. So that was really,
Not yet.
really timely lecture. It was a fantastic presentation by John Conrad, and it was thrilling to actually be able to watch this happen. Actually
Okay, well, hopefully he will.
plow a truck into an asteroid and watch a big plume in it and watch the science work. And so it was really exciting, Bruce. That was a fantastic and timely presentation at that point. Great job. And for those of us who are also here for the first time, just come on up. Don's our program chair. Bruce over here is our
Bruce is
program chair.
Program chair.
And
Vice
And-
President.
and our vice president is sitting right over there. He's kind of hiding behind somebody there. That's Pete Kellerman. Come on up and say hello, introduce yourselves. We'd love to get to know who you are. And for this month, I'm really looking forward to this talk, so I don't want to take up too much time here. He's not on yet.
He's not on
Oh,
yet,
he's
so
not.
take your time.
But this, I think it's going to be a fantastic presentation, so I'm excited to get to. We have one observing event coming up, right?
We have two coming up. We have
Oh.
3 coming up. actually.
Oops, what are they? I know we have.
I'll go over that in my
Okay, great.
presentation.
So I'm going to turn the meeting over to Don at this point, and he'll let us know what's up for the rest of this month, because it sounds like we're going to be a little bit busy. And to the execs out there, we do have a committee meeting coming up on the 22nd of this month. I think we're going to be having it at my place.
Good, good.
So after 2 years and all these COVID delays, I think it's high time that we actually, the executives started doing something here. So, all right, Don, take it away.
All right, I'm gonna share my screen.
Welcome to Port Two. My name is Jim Putnam, and in this video, I'm going to be replacing these Gulfstream
Mute yourself. Please mute everyone.
about 20 years. This is the west side of my house. For those of you who don't know Nandina as well, this is
Angelo, you have to mute. I muted you. So I'm going to mute everybody here. All right,
almost any old varieties, new varieties.
Angelo, you have to mute.
Really take.
How's that?
Got this kind of space.
No, got to mute. Now you're okay. Stay muted. I'm going to give dope slap. Okay, upcoming events. We do have some things happening, as Dave mentioned. First of all, thank you to everyone who came out to Star Farm Park. I was there at the beginning and it looked like we had a great turnout. Probably had 8, 10 scopes, you think, was it?
Yeah.
8, probably 6, 7, 8.
We had 8 plus a pair of binoculars.
Okay, so we had a real good turnout, and I think the township was overjoyed with what happened. So your boss, yeah, did she? Oh, good. Yeah, we this is after getting clouded out for like 3 years in a row, so it worked out really well. So thank you for everyone who came out. It was a success. Now,
A couple people there at telescopes that brought their own.
really,
telescopes.
that's
They
great.
stayed after we left.
Good, good. So our next public event, I mean, all our events are public, but the next one that we're teaming up with somebody on is Wolf's Hollow with the Ackland Public Library. And I've actually already heard today from the Chester County Library wants to do one next spring at Springton Manor. So people are getting back in the groove of doing events. So Friday at the end of the month, Wolf's Hollow. I will send out notice because there's special directions to get there. We're getting in through a special back gate they opened for us. It's not where we set up like 3 years ago. It's a much, much better place. This is a wide open area, a great sky. And so it's really, if you come out and join us, it will be wonderful. So, and the library I know is really talking up this event. So we asked them to limit it to 50 attendees. But I'll bet they get that many. So, and then this Friday we have Bread and Wine Red Clay, and we have another one on Friday, November 18th, if the weather's okay. This Friday is looking good. November, who knows? It could be snowing by then, the way they're talking. So, so I want to do something different here. I want to show you now. Most times I go through the night sky and the things we can see up there. I want to show you real quick. This is actually a different application. If you don't want to download Stellarium, this is a live Stellarium web live on the internet. Okay, it's not a download application, it's live on the internet. And if you watch Derek Pitts, it's a wonderful show once a month on Thursdays. He does a night skies at home, and this is what he uses. So it's a really neat system. You can, of course, do all the things that Stellarium does.
It's not going to be on the computer.
You got to keep yourself muted there, please. Does all the things you do with regular Stellarium. You can go in and see deep sky objects. But I'm not going to do that tonight because, I talk about these things every month, but I don't talk about how to find them. So let me reload this. What I don't talk about is how to find these things. All right, so what I'm going to do, I divided this up into 3 different sections. I can talk about all these in the sky, but if you can't find them, well, what good is it, right? So this sheet is from the Astronomical League. It's about how to find things in the night sky. So I thought I'd go through this in 3 different sections. So there's a series of things how you can find things. First of all, the modern way is to, where's our camera aiming? The first way, they're saying go to telescopes. All right, so if you have a go-to telescope, like some of us have, they all come with a little hand controller. You level the mount, you point the tube toward north, enter the date and time, where you're at. Then you have to find 2 stars. This sheet is a little bit old because now they're much easier. You can now buy a scope, you can set it up, hit a button, and it will find the stars and it will align itself. It'll figure out where it's at. And you can do that for like 500 bucks. Okay. It used to be you have to spend 1,000, 800, 2,000 to get a scope that would do this. So this sheet is a little bit old. In fact, in the newsletter in September, there was an article, essay submitted by Avni, forget her last name, and their last name, a young Indian American woman that's in our student. She's like 14, very brilliant, very bright, and she bought a telescope. I helped her set up, and it was only a couple $100 celestron, and she puts her cell phone in a special spot, and the cell phone figures out where it's at, and it points everything. So that's one way to find things. They call it the modern way. All right, modern way. That's the easy way. Right. If you can buy and figure out how to use one of these things, and they're getting easier and easier all the time how to use. The other way, the way that really matters, is learning the stars and constellations. Okay, no substitute for sitting under the stars with a map and a red flashlight. When we give our classes to every spring, we give a series of 6 classes. One class taught by everyone, different members of our club. When I teach the observing class, I tell them to really enjoy the night sky, there's only 3 things you need to do. First one is to learn the constellations. The second one is to learn the constellations. And the third one is to learn the constellations. It really is the best thing you can do. Okay, once you know the constellations, for me, it's like having several dozen new friends. Okay, once you learn them, they're friends. Like we were at the York County Star Party about 2 weeks ago. And when I saw the Pleiades rising over the top of Pete Kellerman's tent, when I saw the Pleiades, it was like, wow, it's so wonderful to see you again. Now, the Pleiades is not a constellation. Anyone tell me what it is? It's an asterism, which is a part of a constellation. What's the most famous asterism? Big Dipper, exactly right. So once you learn these things, every spring, the Martina glass, yeah, it's a special one. You can make up your own, certainly. You know, and in the springtime, when I see Leo the Lion coming up, my favorite constellation, it's like spring is here. Okay, I know it's getting warmer weather. It's like an old friend I have who moved away for 6 months and now moved back. It's once you learn these guys, it is truly a joy. Okay, so star map, a red flashlight, and just figure out where you're at. Start with well-known stars. So here's how you can also find things in the sky. I think it's in the next page. So you would, with a star map, find the stars visible to the unaided eye, find a pattern, and then we're going to do what's called use your a little scope on top of the telescope, the finder scope. Now, if you look, here's Cassiopeia. You can see it up there. There's Cassiopeia. That's the beta star. Down here is a open cluster called 7789. That's known as Caroline's Rose, and it's a beautiful open cluster. But if you look, here's beta, and here's 779. In the finder scope, what is it? It's backwards, right? It's upside down. You have to make sure your finder scope might be one that inverts the image. So it makes it a little harder. One of the best investments you can make for a telescope is to buy a correct image finder. That way, what you see in the scope, in your finder scope within the sky, it makes it a lot easier. You can work it either way. So that's where you would find it. You would find a bright star, and you would know that heading a different direction, you can find the object you're looking for. In this case, the open cluster Caroline's Rose. And once you get close to it, there it is in your finder. You find beta and you move your scope to there. So why use a finder scope? It's a wide field of view. It's about 5 degrees. You have to make sure they're aligned. You do that during the daytime, so they're looking at the same thing in the sky. If they're not aligned, won't be much help. And but in that little tiny telescope, it's a little scope. You're not going to see everything, but you'll get the brighter objects and you'll get the stars, certainly. So once you find the suitable guide star, like beta CAS, then you can find the object you're looking for. And as they say, finder scope view might be inverted. Buy a correct image finder scope, much better. And what I really like to use is a red dot finder. And I use them all the time. And finally, star hopping. Star hopping is like playing Where's Waldo in the sky. It's so much fun. Okay, and if you don't have a guided scope, it's really the only way to find a lot of these faint objects. So if you remember up ahead, up above here, there's beta and there's 7789. So we would get beta in the scope. Now here's the whole sky image. There's beta, and that's what we're looking for, M108, a galaxy. Now you see there's an angle here. They've twisted this a little bit to make it easier, all right? So even though the angle there is down, the angle here is across. So to star hop, once you get this in your field of view, you would say, all right, I know I need to go somewhere that way. How do I get there? You would cite something like, in this case, you would cite this star on the left-hand side of the field of view. Then you move your whole field of view to number 2. You know where you were. Okay, you know you saw this one in this field of view. Now you've centered there and you find the next thing you're going to go to. So if once you know where you are from this star to this, then you can, all right, where's my next leap? All right, I'm going to hop over here next. So when I hop over here, I put what was in the left-hand side of my view in the right-hand side. So you're hopping from one to the next. Every time you do, now we have these in the right hand, I find something in the left, and then I hop and put them in the right. And there you find M108. Now you need a good star chart to do this. If you don't know the stars, you can't star hop. So you need a good star hop, a good map, or an app. Best thing is one of the Sky Safari apps on a tablet or your phone. Probably a tablet is a better field of view. And I don't know if this is a typo or not. It says hope among the stars. I think what he meant was hop among the stars. Or if it's a cloudy night, you would have hoped you got stars, right?
Thank you.
So each field of view, you go one at a time and star hop from here to here, keeping track of what you saw on one side, put it in the other side, one hop at a time. It's a lot of fun. It really is. It's like finding treasure in the sky. It really is like that. So you know, I have go-to telescopes. I love them, but I like star hopping better than anything. Kathy?
Turn left to Orion does exactly that.
Yeah, the book, Turn Left to Orion. Yeah, yeah. So that's all I had. Let's see if our presenter is logged in. Ah, Kevin's here. Good. Kevin, I can turn it over to you.
Excellent. Can you hear me okay?
We can hear you fine. Yep. We're gonna let Bruce introduce you real quick.
Hi, everyone. Yes.
Mention one thing. The 27th through the 30th is the South Jersey Star Party.
Okay.
I may be there myself. Unfortunately, it conflicts with Apollo.
Right.
But
Right.
it's a nice little party. Star party. I haven't been to it since the pandemic, so I don't know how it's going to be this time around.
All right, and I can send out notice of that. To the
It's
member.
over Bell Plain
Yeah, it's not real far.
Park, and yeah.
Yeah. Probably an hour and a half, 2-hour drive. Okay. Okay, Bruce, you're up.
So, hi, everyone. Tonight it's a real pleasure to introduce to you Dr. Kevin Hand. Dr. Hand's a planetary scientist at JPL, Caltech, and his work focuses on the large evolution of life in the solar system. Particularly, he focuses on Europa's moon, Jupiter's moon, Europa. So given the nature of his interests, his work, both theoretically and in the laboratory, really studies the chemistry and the physics of the icy moons in the outer solar system, specifically those icy moons that may harbor subsurface ocean. So to say that Dr. Hand has a distinguished career, understatement. Just a brief bio. He served as a co-chair for the Europa Lander Science Definition team. From 2011 to 16, he was the deputy chief scientist for the solar system exploration at JPL. He is a co-lead or co-PI on the Europa Clipper mission and a co-PI on the Titan Dragonfly mission, and a member of the National Committee on Astrobiology and Planetary Science. So, you know, pretty impressive career. What's really cool is for a guy who studies the outer solar system, he's gone through some of the most remote
and extreme places on Earth. The dry valleys of Antarctica, the sea ice of the North Pole, glaciers of Kilimanjaro. He was on board James Cameron, 2012 dive into the Marianas Trench, and he was part of a 2003 expedition to the hydrothermal vents in the Atlantic and Pacific Oceans. He stayed 9 dives at the bottom of the ocean. It's pretty impressive. So tonight, or I should end by saying, 2020, he published a book, Alien Oceans, The Search for Life in the Depths of Space.
Bruce, hold it up here.
This book earned me the Nerd Dad of the Year award. And for reading it on the beach at Rhode. Okay. So having said that, this title tonight is in fact the title of the book, Alien Oceans, The Search for Life in the Depths of the Ocean. So Dr. Van, welcome.
Excellent. Thank you so much for the kind introduction, and a pleasure to be with you all virtually. It's fun hearing about some of the events and everything. I grew up in the Green Mountains of Vermont, and the reason I am where I am now is because I looked up at those stars above under the clear night sky of Vermont, and just followed my imagination. And now I'm out at JPL. I used to go to Stellafane, if any of you have ever made it up to Stellafane up in Vermont, and used to run the observatory up at Dartmouth College, where I did my undergrad. We had a 9-inch refractor up there, and the college gave me the keys to the telescope. Very few students were interested in it, but because it was not that well paid attention to, I got the keys in the office and just could sleep up there and use the telescope whenever I wanted. So great to hear about all the observing events going on. So let's see, I'm gonna try to share my screen here. Hopefully this will work. And how's that coming through, Bruce?
Good.
Excellent.
Can you go? Don, is that the full?
Need to view to get a little bigger,
I can't quite hear if there's a question being asked. I can't
We're
quite.
trying to make your view a little bigger. Let me try
Try
that.
to make your screen bigger.
Okay.
Yeah,
That's
good.
better.
Very better. Great.
Okay, good. We got it. You
It's
look
all
good.
yours.
Excellent. Oh, actually, what the I don't know if you can still see me, but this background painting is called Starry Pastures, and it's was done by the same guy who does the Ben and Jerry's cows. Just a nice picture of the night sky in Vermont with a bunch of cows. Okay, well, as Bruce mentioned, so I'm going to talk to you tonight about alien oceans and the search for life in the depths of space. Thank you, Bruce, for reading the book, and those of you who are interested in this topic, I encourage you to check it out. I put my heart and soul into the book, and then it came out in April of 2020, and so all of the publicity and travel to various book stores and stuff was all canceled because of the pandemic. It has done well nevertheless, but yeah, really kind of difficult putting your heart and soul into something and then a global calamity crushes it. But it's a good read. Hopefully you'll find it to be a good read. Now, despite the fact that I'm going to be talking about the search for life and aliens, I do want to keep your expectations at the right level. Tonight, I will not be talking about UFOs, alien abductions, ET, or any kind of plushy alien creatures from distant planets. When I talk about the search for life elsewhere, and for that matter, most of the time when JPL or NASA talks about the search for life elsewhere, we're talking about the search for even the tiniest of microbe. Such a discovery would truly revolutionize our understanding of life in the universe and our place in it. And the story of the search for life beyond Earth is in part the story of our beautiful blue marble reaching out with our robotic spacecraft and our telescopes to search for signs of life. And this amazing diagram shows a line for each of the spacecraft that have been launched by the various space agencies around the globe to various targets. And you can see that there are many lines to our moon, many lines to Venus and Mars, even a few out to the sun and Mercury. But there are very few lines, very few spacecraft that have made it out beyond the asteroid belt. And by merit of these few spacecraft with names like Pioneer, Voyager, Galileo, and more recently New Horizons and Juno, we have made what I would consider to be one of the most profound of discoveries in the past roughly 60 years of solar system exploration. And that discovery is that we now have good reason to predict that liquid water oceans exist beyond Earth. Shown here is what I like to call the portrait of the ocean worlds of our solar system. At the center, of course, is the ocean of the Earth, the ocean that we know and love and need to protect. And then around the Earth, I've placed Europa, Ganymede, and Callisto, 3 moons of Jupiter, and Titan and Enceladus, 2 moons of Saturn. And I've even got Neptune's curious moon Triton here. These moons are covered in ice, and in the case of Titan, it's got an atmosphere above its icy shell. And beneath their icy shells are vast, potentially global liquid water oceans that exist today, and as such present incredibly compelling locales to explore and search for life beyond Earth. And these worlds are really transforming our understanding of what it takes for a world to be habitable. In the early days of astronomy and planetary science and astrobiology, our conception of habitability was really framed by kind of a Goldilocks scenario of Venus, Earth, and Mars, and the respective distances of each of these planets from our sun. And the thinking went that in order to be habitable, you had to have liquid water on your surface. You had to have an ocean in contact with an atmosphere. And in order for that to be possible, you had to be at just the right distance from your parent star so as to maintain and sustain enough energy to make that surface ocean possible. If you were too close, like Venus, you got too hot and boiled away any ocean that you may have once had. And if you were too far away, like Mars, you eventually got too cold and lost any liquid water that you once had. Now, the story of Venus and Mars and their liquid water histories is much more complicated than what I've just framed, but suffice to say that these ocean worlds of the outer solar system are teaching us that when it comes to habitability, this is an old Goldilocks. There's a new Goldilocks for habitability, and it's one wherein the energy for maintaining and sustaining liquid water oceans comes not from your parent star, but rather from the tidal tug and pull that various moons can feel as they orbit giant planets, such as Jupiter. Shown here is the innermost large moon of Jupiter, Io. And this inset, an image taken by the Cassini spacecraft as it flew by Io, shows how powerful, how much energy there is in the tidal energy squeezing and tugging and pulling of these various moons. Towards the north pole of Io, you see this umbrella feature. That is a volcanic plume from a volcanic eruption occurring on Io. Io is the most volcanically active body in our solar system, even more volcanically active than our own planet Earth. And the reason that Io is so volcanically active is because of, as it orbits Jupiter, it is squeezed like a ball of taffy, and that mechanical energy turns into internal heat, and that heat then drives these volcanic eruptions. And so the four large moons of Jupiter, which I'm sure many of you have seen, hopefully recently through telescopes and binoculars, the four large moons, Io, Europa, Ganymede, and Callisto, present a sort of new Goldilocks for habitability. And Io in this new framework is kind of like Venus. Io has too much energy. It lost any water that it once had. And the orange and red and white and black that you see, that's all due to various sulfur and iron compounds from the lavas and eruptions of Io's volcanoes. The outermost moon, Callisto, is kind of like Mars in this comparison. Callisto, we think, may have some liquid water in it. It may have an ocean. But right now, our understanding of the tidal energy on Callisto is a bit incomplete. If Callisto does have a subsurface liquid water layer, it's likely maintained through radiogenic decay of heavy elements. And Callisto's ocean, if it does have one, is trapped beneath a very thick ice shell and a very old ice shell, as evidenced by the pockmarking of all the craters that you can see on Callisto's surface. But Europa and Ganymede, and Europa in particular, may occupy this new sweet spot for habitability, this new Goldilocks zone, wherein it has just the right amount of energy input, in this case, tidal energy as opposed to solar energy, so as to have a subsurface liquid water ocean maintained through that tidal heating, and also capped off by an ice shell that helps protect it from the cold and dark of space. And so Europa, the moon on which I focus a lot of my time, we think is in kind of this new sweet spot for habitability. And tonight I'll focus in on Europa, and then we'll travel out to Enceladus. Actually, we'll go to Enceladus first, and then Europa, both moons of which have significant tidal energy sustaining liquid water oceans. And of course, just to reemphasize, part of the reason why these oceans are so compelling is because if we've learned anything from our search for life, if from our exploration of life on Earth, it's that where you find the liquid water, you almost always find life, whether it's life in extreme environments, down at the bottom of our ocean, or in the hot springs of the Rift Valley shown at the upper right, or down in the dry valleys of Antarctica where there's transient liquid water for a few days of each year. Life requires liquid water, from life in extreme environments to life of extreme lifestyles. We all depend on liquid water. And I like to show this montage for another reason, and that is because for all of the diversity of life on Earth, from microbes at hydrothermal vents to Mick and Keith being perhaps the most extreme of humanoid life forms, we are all connected by the same tree of life. All of the microbes and single-celled organisms, all of the humans, all of life as we know it on Earth is all connected by the same tree of life. And think about it, our tree of life has really transformed very dramatically over the same period in which we've really advanced our exploration of the solar system. This is what our tree of life looked like back in the 1950s with trilobites and dinosaurs and Neanderthals all occupying this kind of branchy tree, to now a tree of life based on genetics. This is the 16S RNA tree of life that binds us all together. Bacteria dominate archaea, and then the eukaryotes, us, we're down here in this tiny little, we're a little twig down here. Keith and Mick and all of us would be just a tiny little piece down past that opus Thoconta eukaryote. And so part of what excites me about the search for life on these distant alien oceans is the prospect of discovering a second independent origin of life, a second independent tree. And the possibility of there perhaps being life based on something other than DNA, RNA, and proteins. Is there some other game in town, some other way to get the business of life done? And these worlds offer locales through which we can actually search for living life, extant life. And that's really important because in comparison to our search for life on Mars, and I love Mars, I work on the Perseverance rover. It's a fantastic mission and we're going to be returning samples. But for all of the beauty of the geology and potential evidence for past life on Mars, we are never going to find in the ancient rocks of Mars traces of DNA or RNA or some ancient large biomolecule that tells us about past life on Mars. The large molecules of life do not last in the rock record. We see that on Earth. DNA only lasts tens of millions of years, RNA, et cetera, a similar time frame. The ancient evidence that we have for life on Earth, the traces of life going back billions of years in the rock record on Earth, all comes from small aromatic compounds that are circular rings of carbon that are relics of ancient membranes. And so we have molecules from membranes of old bacteria and archaea from rocks found in Greenland and Australia and South Africa. And as exciting as that evidence is for ancient life on Earth, and as it would be for ancient life on Mars, it's not going to tell us about the detailed biochemistry. We're not going to be able to build a tree of life from that information. But on these alien oceans, life could be alive there today. And if we were to find it there, we could actually construct a new or related tree of life. We could learn whether or not the origin of life is easy or hard, whether or not life arises wherever the conditions are right. And these worlds, the exploration of these worlds, would help inform our understanding of what conditions are required for life itself to originate. And were we not to find life on these worlds, that would also inform our understanding of how life on Earth arose. On these distant worlds, life would have to arise within hydrothermal vents or within the ice. It could not have arisen on ancient seashores. There's no continents or beaches on Europa or Enceladus or Ganymede, Callisto, or Titan for that matter, although Titan's kind of a different case with organic solvents. Were we not to find life on any of these worlds, I think we would have to conclude that life on Earth most likely arose on ancient seashores where the ocean lapped upon the proto-continents of our young planet. So that sets the stage for why these worlds are so scientifically compelling. Now let's get into the science of some of these worlds. And as I mentioned, I'll tonight just focus on Enceladus and Europa. Now, how do we think we know that these oceans exist beyond Earth? Much of it, of course, begins with a robotic spacecraft. And shown here at left is the Cassini spacecraft in the spacecraft assembly facility at JPL. And at upper right is the Galileo spacecraft, as photographed by the astronauts on board the space shuttle from which the Galileo spacecraft was deployed. Now, of course, no spacecraft would be of any value if we could not receive the signals back on Earth. And that's where the Deep Space Network, one of the antennas of which is shown at the bottom right. These are our ears on the ground, and they allow us to collect the data that we can reconstruct into beautiful images like this. Here, of course, is Saturn shown with its beautiful rings. And along with its rings, Saturn is mother to a beautiful assortment of curious moons. One of the most curious of which is Enceladus, shown here with Saturn and the rings behind it. Enceladus is not a large moon. It's about 300 miles or 500 kilometers in diameter. That's about the distance between Chicago and Cleveland. And on closer inspection of Enceladus's ice-covered surface, your eye is drawn to a curious pattern. To the north, Enceladus is covered with craters. And craters, to a planetary scientist, are an indication of an old surface. It takes time for craters to accumulate. And so some publications working from the crater counts and the crater dimensions and population indicate that Enceladus's northern region may be as old as 3 to 3.5 billion years old. But to the south, we see essentially no craters, and we also see these tiger stripes cracking across the southern hemisphere of Enceladus. And when the Cassini spacecraft returned this image, the science team was, of course, captivated and urged the engineers to give us a flyby where we could actually see these fractures at just the right angle so we could detect whether or not anything was coming out of these fractures. So shown here are those jets erupting out of the fractures. And I'm sure many of you have seen this image or images like this before, but hopefully if I were in the room with you, I would be hearing some oohs and ahs, because this is in fact one of the most stunning pictures that has ever been taken in the history of solar system exploration. Shown here are jets of water erupting out of those fractures. And along with images like this, the Cassini spacecraft was also able to collect some of the material from the jets during a few of its closest flybys, which were in the range of 100 kilometers above the surface. And the Cassini spacecraft was able to determine some of the composition of these jets, and I'll get into that in just a minute. But looking down directly upon these tiger stripes, it's not, this is not like looking down at a snowmaking machine where you can clearly see an abundance of eruption coming out. This material is quite diffuse. And in this image, to the in the middle, towards the bottom, you can see sort of a softer region with a dark a hole in the middle. That may well be the site of a plume erupting, and that soft region around that dark, those couple of dark holes in the fractures could well be snow, Enceladian snow, that has softened many of the fractures around the region of the eruption. So as I mentioned, the Cassini spacecraft was able to sample and taste the plumes with 2 mass spectrometers that it had on board. And with the first mass spectrometer, the ion and neutral mass spectrometer, shown in the upper left, the data revealed that not only was there water vapor, but also methane, some simple organics, some carbon monoxide, some fragments from more complex organics, and some carbon dioxide. And as exciting as this evidence was, it did not necessarily point directly to a subsurface ocean. Many scientists, myself somewhat included in that, wanted to proceed with caution on the interpretation of this data, because of course we know of icy objects that have jets and also have organics. Comets are well characterized as objects with jets where material is expelled from them, and some of that material includes quite an array of organics. But with subsequent flybys, the other mass spectrometer, the dust analyzer on board Cassini, was able to reveal that not only are there organics emanating from these plumes, but there are also salts. And in that mass spectrum that you see in the middle and in the cartoon shown at upper right, you can see that potassium, sodium, and chlorine were all detected in that mass spectrum. That to me was very compelling. We don't see salts coming out of comets. And the reason is that salts are derived from liquid water leaching through silicate rocks. And that's what's shown in that diagram or that cartoon at upper right. When you have liquid water leaching through rocks, you can extract salts. And so with this kind of data, many of us moved from skeptical to accepting the hypothesis that in fact these jets were connected to a liquid water ocean beneath the icy shell. And then in some of the final flybys of Enceladus that Cassini made, silica was revealed, silicon plus oxygen, and that's what's shown at bottom right, and then also an excess of H2, molecular hydrogen. And this data, along with the previous data, helped point towards not only a subsurface liquid water ocean, but also a liquid water ocean that likely has an active seafloor, a seafloor that might look like this. Now, this, of course, is not an image of Enceladus' seafloor. This is an image of our ocean seafloor. This was actually part of that expedition that Bruce mentioned that I was part of back in 2003. This is a hydrothermal event several kilometers beneath the surface of our ocean. And the type of chemistry that emanates from some hydrothermal vents is consistent with the silica and hydrogen excess that we observed around Enceladus. And so our conceptualization of Enceladus at this point in time is that it's got this icy shell, and that icy shell is perhaps tens of kilometers in thickness. Perhaps it's a lot thinner near the South Pole. Those fractures near the South Pole connect to a liquid water ocean of perhaps several tens of kilometers in thickness. And then that ocean is underlain by a silicate seafloor of undifferentiated material. We do not think that Enceladus has an iron core or differentiate or had enough energy to differentiate during formation and subsequent tidal evolution. And that's why you see that kind of matrix of white and black material in the interior of Enceladus. But nevertheless, we think that geologic processes that can drive hydrothermal events like serpentinization might be sustaining an active, potentially chemically dynamic system that could help give rise to and sustain life in that ocean. Let's move to Europa. Europa is a much larger moon than Enceladus. Europa is about 3,000 kilometers in diameter. That means that it's about the size of our own moon, shown here to scale with respect to the Earth, all of which are then shown to scale to Jupiter. And Jupiter is some 318 times as massive as the Earth. So just imagine, we all know the tidal cycle on Earth and how tides go in and out because of the interaction of the Earth with our moon. Now imagine that you're Europa orbiting Jupiter, and given the 318 times as massive as Jupiter is, Europa is just getting squeezed again like a ball of taffy. And in fact, some predictions are that if you could stand on Europa's surface, you would rise by about 100 feet with each diurnal, each day and night cycle of that tidal tug and pull. So how do we think we know that Europa has an ocean? Well, unlike Enceladus, the Galileo spacecraft that flew by Europa numerous times did not observe any dramatic plumes erupting out. And that's not too surprising. Given Europa's increased gravity, Europa's gravity is about 1/7 of the Earth's, and so Europa's gravity is much more akin to the moon's gravity. Any plumes that erupted would be pulled back down and would not extend out for the many hundreds of kilometers that were observed on Enceladus, where the gravity is so low that it's more akin to a large asteroid than a large moon. But nevertheless, despite the fact that we do not have very strong evidence for plumes, I put a little asterisk by that because I'm on a Hubble team where we've actually found some evidence for plumes at Europa. But nevertheless, there are several lines of evidence for Europa having a subsurface ocean. And I like to break this down into 3 easy pieces. The first piece of the puzzle is to find a rainbow connection. What do I mean by that? Well, I'm a spectroscopist, and spectroscopy, for all intents and purposes, is the study of rainbows. As you all appreciate, you turn a rainbow on its side and you have a spectrum of light from our sun and various absorptions made by the water as the sunlight refracts and reflects off of the water drops. And you can actually learn about the composition of our sun and of our atmosphere by studying rainbows. Spectroscopy or rainbows can also be collected of distant planets, and this is a spectrum collected of Europa by the Russian astronomer Vasily Moreau back in 1964. Actually, not too long. So this is October 1st, 1964. And this spectrum, with its stepwise progression downward from 1 micron to 1.5 and 2 microns, is highly diagnostic of water ice. And so Galileo discovered the large moons of Jupiter in 1610, and some 350 years after that, we now know that by merit of spectra like this, that Europa is a moon covered in ice. That's the first piece of the puzzle. The second piece of the puzzle is to babysit a spacecraft. And the spacecraft, the baby in this case, is the Galileo spacecraft, shown at right. And there again is the Deep Space Network. And by very carefully monitoring the position of a spacecraft as it flies by a planet or a moon, you can get information about its moment of inertia and its interior. Now, shown here is a lot of math, but this is beautiful physics. It's physics 101, where many of you probably recognize the gravitational force equation up there near my little sketch of the Galileo spacecraft. And really, the gravitational force equation is derived from the gravitational potential equation, the expansion of which is shown in the middle. And then I kind of detail out the moment of inertia, I. And what all this means is that as a spacecraft flies by, in this case, Europa, as the Galileo spacecraft flew by Europa, it was ever so gently, or perhaps not so gently, sped up and slowed down by the gravity of Europa. And that caused a blue and a red shift in the transmission of the signal back to Earth. And so through that slight blue and red shift of the transmission of the data as Galileo flew by Europa, the gravity team, the team looking at this data, was able to figure out the moment of inertia for Europa. And from that, was able to figure out that the interior of Europa did in fact consist of something very heavy, best fit by an iron sulfur core, over which was a less dense layer of rocks and silicates. And then over that, what the gravity data revealed is that there was a very low density layer, a layer that was best fit by a density of about 1 gram per cubic centimeter. And the material that best fits that density profile is water. Now, the gravity data is insufficient to tell the density difference between liquid water and ice. And so the gravity data left us, the second piece of the puzzle, left us with a water layer on the surface of Europa in either liquid or solid phase. Now, of course, we knew that the surface itself had to be ice from the spectroscopy, and also just by the physics of how cold space is. But that at least opened the doorway to there being some subsurface liquid water down to about a 100 or 200 kilometers depth. So that gets us to the third piece of the puzzle. And here I'd like to make the analogy to adhering to airport security. And my apologies that this image is a little blurry. I took it at the JFK airport and I was trying not to get arrested for suspicious activity. But the reason I took this picture is because when you walk through one of those doorways at an airport, you are walking through a time-varying magnetic field. And that time-varying magnetic field induces electric currents in any conductor that you might have in your pocket. And those electric currents in any metal or conductor that you have in your pocket then gives rise to what we call an induced magnetic field. And around that little doorway are special sensors, magnetometers, that can detect the induced magnetic field created by the metal in your pocket. And if anything is detected, the alarm goes off and you get pulled aside and given the pat down. Well, out at Jupiter, when Galileo flew by Europa, the alarm went off. And what I mean by this is that in the analogy to airport security, Jupiter and its rotating magnetic field are kind of like the metal detector that you walk through. You are kind of like Europa. And in this case, the field, they're both, you're walking, Europa's orbiting Jupiter, but imagine the metal detector moving also. But essentially there's a time varying magnetic field created by Jupiter's magnetic field. And so you as Europa are subject to this time varying field. And then the detector or the alarm went off because what the magnetometer on the Galileo mission revealed is that there is an induced magnetic field around Europa, and that induced magnetic field requires some sort of conductive layer in the pocket, so to speak, of Europa. Now, shown here again is a bunch of E&M equations, Faraday's law, and I won't get into this in much detail, but it's beautiful physics. Just briefly, up at the top left, that's Jupiter's magnetic field, which is tilted by almost 10 degrees relative to the rotation axis. And at bottom left, that tilt of the magnetic field causes there to be a time varying component of the magnetic field, a dB dt, so to speak. And Europa experiences that. And that's kind of like you walking through the metal detector. And so when the alarm went off and the induced magnetic field around Europa was observed and measured multiple times on multiple flybys, the question became, well, what could be that conductor? Well, as we know from the first two pieces of the puzzle, Europa's got an iron core. Iron is quite conductive. Could it have been iron that provided this induced magnetic field? It turns out that the iron core is too small and too far away, essentially, from the spacecraft to explain the magnitude of the observation. And I did a lot of work on this during my PhD and noodled around on all sorts of permutations, and I could not really get the core to explain the data. Then you can ask, well, what about that silicate mantle, those rocks above the core? It turns out that silicates, the rocks that we walk on, the rocks of our crust and mantle, are not that conductive. So they too could not explain the data. Well, what about an icy shell? It turns out that ice is not conductive enough to explain it. But a liquid water ocean, and in particular, a salty liquid water layer trapped beneath the icy shell, beautifully explains the Galileo magnetometer data. And so it's through that third piece of the puzzle that we can connect the icy surface of spectroscopy, the water layer extending down to some depth as revealed by the gravity data, and then finally, with the detection of this induced magnetic field, an ocean that is some 100 kilometers in depth, trapped beneath an ice shell of 10 to perhaps 20 or so kilometers in thickness. So here's what Europa may well look like in cross section. Even though we have not observed plumes or and the Hubble data is still a bit equivocal, I do think that plumes likely exist on Europa. They just don't erupt as dramatically as they do on Enceladus. And there's a lot of interesting geology and ice physics going on in Europa with different formations, many of which we do not see on Enceladus. Here, for example, is one. This is a CCAS feature on Europa. The scale here is about 30 miles across. And if I were to show you this image and say this was a picture of Antarctica or Greenland here on Earth, you'd probably say, yeah, that makes sense, except for perhaps that reddish color. These look like icebergs having broken off of an ice sheet. But we know that they cannot be drifting along in some warm ocean or ice. These icebergs, so to speak, are at 100 Kelvin or about minus 280 degrees Fahrenheit. We do not know what is allowing these plates of ice to kind of drift, fracture, and break. But you can see that they kind of form a puzzle piece network where you can connect back a bunch of these fractures and kind of put Humpty Dumpty back together again. Here's another dramatic example of Europa's icy surface. This is at a bit of a larger scale. We see these fractures, these lineaments, and also some dimples or freckles, such as that little dome and reddish feature near the center. We don't see features like this or quite as extensive as this on Enceladus. Some other kind of icy geology is driving a lot of the morphology, the shape of what we see on Europa. Coupled with that, as can be evidenced by this image here, there's this reddish, yellowish, brownish color that's often associated with features that we think might connect to the ocean below. These bands and linnea that you see here and that freckle feature near the middle, they seem to be a bit of a source of this darker reddish material. And this was a question that captivated myself and my colleague Bob Carlson, and we decided to investigate it in the laboratory. So this is part of our lab, the Ocean Worlds lab at JPL, where we can recreate Europa and Enceladus at the microscale and a bit more at the macro scale. Shown here is what I like to call one of our Europa in a cans, where I can bring samples down to pressures and temperatures similar to Europa's surface. There is no atmosphere on Europa. When I say pressure, I essentially mean the vacuum of space. And as I mentioned, the temperature of the surface is about 100 Kelvin. And in this particular experiment, and then to top it off, on top of the chamber is an electron gun. Europa's surface is bombarded by electrons and ions and protons from Jupiter's magnetic field. And so in this particular experiment, I was curious as to whether or not some of the reddish material might be salts from the ocean below. And spectroscopically, salts had kind of eluded us because salts like sodium chloride have no real distinct absorption features. Shown here is sodium chloride. You all know and love it as table salt. This is reagent grade, lab grade sodium chloride. It's flat white to the eye, and it's also spectroscopically flat. So you can't really detect it by collecting a spectrum of the surface. Now, having said that, after putting it in our chamber and irradiating it and pulling it out of the chamber, this is what we saw. A beautiful caramel brownish color, which, you know, my jaw dropped when I first saw this, because of course this looks somewhat similar to that discoloration that we see on Europa's surface. And so after doing these lab experiments, I teamed up with my colleague Mike Brown and Samantha Trumbo down at Caltech, and we got time on the Hubble Space Telescope. And with Hubble, we were able to collect spectra of Europa's surface, shown here at the upper right. The black jagged line is the Hubble data. And then the red line that you see there is data from the experiments that I did. And it turns out that after irradiation, not only do you get this discoloration that's visible to the naked eye, you also get these absorptions at very specific wavelengths, in this case, around 450 nanometers. And that absorption is highly diagnostic of this irradiated sodium chloride. And it's just a beautiful culmination of hypothesis, lab experiment, getting the time on Hubble. And sure enough, there's this absorption showing us that there is, in fact, salt on Europa's surface. So here is a mosaic of the highest resolution images we have of Europa's surface. This is about 6 meters per pixel. These are just a few postage stamps of images collected by the Galileo mission. This is a black and white image. Were this in color, a lot of the material that you see in gray and black would likely be red, yellow, brown, and I think attributable to salts. Some of it could well be also organics or even life brought up from the ocean below. The cliff shown here is perhaps a few hundred feet in height, and the talus that's forming the dark band at the bottom could well be teeming with evidence of life from the ocean below. So where are we going? Well, the next step for Europa exploration is the Europa Clipper mission, which will launch hopefully in October of 2024. And ESA also has the Jupiter Icy Moons Explorer, shown at right. The Europa Clipper mission will go into orbit around Jupiter and will fly by Europa some 45 times. The JUICE mission will fly by Europa a couple of times and Callisto a few times, and then it will go into orbit around Ganymede. So that's these missions will arrive at Jupiter and go and begin their flybys in the early 2030s. I did not spend time tonight on Titan, but Titan has the Dragonfly mission, which is an octocopter that will parachute down through the atmosphere, eventually getting rid of its parachute, and then land on the surface like a drone that have become quite popular on Earth. We will then examine the dunes and mid-latitude region of Titan, and we'll take several hops investigating a few different regions on Titan's surface. And then the mission that I've been helping to lead for much of the past decade and a half is the Europa Lander. Sadly, this mission is essentially canceled. So the NASA has no plans to proceed at this time with this mission. This is quite disappointing. This is after roughly $300 million of investment in the mission. And we made a lot of progress on this mission at JPL. Here's an animation that's based on a lot of our CAD models. So this is actually a high fidelity. It's not just a pretty animation. This is all backboned by detailed CAD designs. And so what you're seeing here is the lander plus its descent stage coming out of the biobarrier. That's a protective shell that the spacecraft is put in after being baked out to make sure that there are no microbial hitchhikers. We take planetary protection very seriously. After deployment from the carrier stage, the spacecraft then does a deorbit burn with the Star 38 motor, and that burn is shown here. A few trajectory correction maneuvers by the smaller thrusters also shown. We then get rid of that Star 38, and the lander itself then uses the sky crane approach to landing on Europa's surface. The sky crane, as you may know, was used for landing Curiosity and Perseverance on Mars. And as part of the Europa Lander project, we invested in terrain relative navigation on Perseverance, which helped that mission avoid crashing into large boulders and other hazards on the surface. And so we now know that terrain relative navigation works and could be used for landing on Europa. Once we get to the surface, we take an image of the surroundings, and then on board inside the spacecraft is a suite of instruments that will analyze the chemistry and look for biosignatures, look for complex organics within the material collected by the robotic arm. There would have also been a microscope to look for any cell-like structures in the material collected. And there also would have been a seismometer to listen to the ice shell and search for any signs of Europa quakes. The acoustics of those Europa quakes could have told us about the thickness of the ice shell and the thickness of the ocean itself. But sadly, as I mentioned, we are no longer moving forward with this mission. I'm not quite sure what we're going to do, but it's not on NASA's list of prioritized missions for the near future. But now I want to transition and finish up just by talking about a bit of exploration on Earth and how our exploration of Earth's cryosphere and ocean is helping guide our exploration of these alien oceans. And I'll take you to just two places on our beautiful home planet. First, we'll travel to Antarctica. And in particular, we'll go to Casey Station, which is part of the Australian Antarctic Territory, shown here. I was down there in late 2019. It was an incredible team down there. The Australians are just a blast to work with. As you can see, they have this signpost for Casey Station with the distances to places all around the globe. And they kindly created a signpost for Europa, shown at bottom. And you, as astronomers, will all appreciate that technically we shouldn't have had the sign pointing in that direction, because really Europa would have been much closer to the horizon. But we thought for nothing else than comedic effect, it was best just to point upwards, because that, of course, is the direction of the stars. We were down in Antarctica, a small team from JPL and a few colleagues from Australia itself, to test out our buoyant rover for under ice exploration. No, our team did not consist of penguins, but the penguins greatly enjoyed observing our activities and doing checks to make sure that we were safe and secure in our robotic deployments. So this particular robotic vehicle is designed to rove on the underside of the ice so that we can investigate the ice-water interface and any biology or chemistry at the ice-water interface without disturbing it. Normal ROVs have thrusters and they destroy the algal mats and other things that you see at the ice-water interface. And they also take a lot of battery power to kind of position at the ice-water interface. Meanwhile, with this vehicle, we can just rove and then stay stationary wherever we end up wanting to investigate. And so these are the kinds of things that we saw, algal mats and excess oxygen trapped under the ice and fish feeding on the algal mats. Our hope is to someday leave the rover underneath the ice for the entire Antarctic winter so that we can see how these microbial communities live and die as the Antarctic winter advances. But during our deployment down there in 2019, we only deployed the vehicle for a few days, but it was a beautiful and very successful test of the capability. The next place I want to bring you is to the deepest point in our ocean. That is the Mariana Trench, and in particular, the Challenger Deep and a site not too far away from the Challenger Deep called the Sirena Deep. As Bruce mentioned, in 2012, I was part of the James Cameron and National Geographic and Rolex expedition to return to the Challenger Deep, a site of about 7 miles or 11 kilometers in depth that had not been visited by a human since the Trieste expedition of the Navy back in 1960. And so James Cameron is quite the ocean explorer, and he helped build and fund the construction of the Deep Sea Challenger shown here. This is a human occupied vehicle that has room for just one human. And Jim made it up and down alive, much to the relief of our whole team. But tonight, I'm not going to focus on the human operated vehicle, but rather I'm going to highlight some of the simple robotic vehicles that we deployed throughout the Mariana Trench. And in particular, we let one sit at the bottom of the Challenger Deep for upwards of 10 hours, during which time we saw that in the deepest, darkest depths of our ocean, out of this dark abyss came these life forms, these amphipod shrimp-like creatures. And you can see on the end of this robotic arm of the robotic vehicle here, there's a net. And within that net is a fish head. And so the amphipods came out of the darkness to feed on this fish head. And that is just amazing. This is the one of the harshest environments on our planet. And it turns out that the pressure of the Mariana Trench is very similar to the pressure in Europa's ocean. And so by finding microbes and larger organisms alive in this area, we gain some foothold of confidence in that if life can survive here, it can almost certainly survive if it has originated. It can almost certainly survive and potentially thrive in the deepest, darkest depths of Europa's ocean. Now, up close, as beautiful as these things are swimming in the abyss, it is a face that only a mother can love. And after dissecting one of these and getting a closer look, and I get this question all the time, what do they taste like? But after dissecting one of the engineers on board actually grabbed one and ate it. It was part of a bad dare. And I say a bad dare because within minutes of eating this creature, this gentleman, to put it politely, went to the side of the ship and returned the creature from the ocean from whence it came. Now, of course, the observation of those amphipods was quite exciting, but as I mentioned, the amphipods came out of the darkness and were feeding on that fish head. That left a question of, well, what are those amphipods eating when there's no bait trap around? And we think we got the answer to that question with a second drop that we did in the Sirena Deep. And shown here is that robotic arm coming down. And at the Sirena Deep, we happened to land not at the deepest part of the Mariana Trench, but just upslope a bit. And serendipitously, we landed near an outcrop. And to a marine geologist, this image also deserves an ooh and an ah, because no one had yet seen outcrop or even rocks at this depth. And upon closer inspection of these rocks, what we saw is that not only is there interesting geology here, but there are also these filaments dangling off of these rocks. And to the trained microbiology eye, these filaments are the canary in the coal mine for microbial mats. And we're able to get a sample of these mats, we think, by some of that material that then drifted into the sampling mechanism that we had at the end of the robotic arm. And I analyzed those samples and we found microbes that could well be responsible for these putative microbial mats. So we think when the fish heads, the bait trap is not there, the amphipods are feeding on these microbial mats, and these mats are eating the rocks. They are forming the base of a chemosynthetic as opposed to photosynthetic food chain. So somewhat akin to the hydrothermal vents, but a much more mild form of a geochemical reaction driving and sustaining these microbes. So again, the exploration of our home planet and the discovery of ecosystems like this give us hope that someday in distant alien oceans, we may well discover life beyond Earth. And I'll finish with this animation that's also from that IMAX movie, Aliens of the Deep. This is kind of my dream of dream missions. This would follow on, landing on the surface. This mission involves a melt probe. And with a melt probe, you have a cylinder with a heated tip or a drill on the surface. And this melt probe would then allow us to get through the ice, leaving behind a fiber optic and some acoustic modems so we can relay data to the surface. Once it gets to the ice-water interface, we then deploy an autonomous underwater vehicle. It would have to have a lot of intelligence. We're not going to be able to joystick this from JPL. And then we go down and we find hydrothermal vents. Again, this is my dream of dreams. And we find not only microbes, but we also make contact with beautiful alien jellyfish-like creatures, and we change our understanding of life in the universe forever and ever. So I'll close with just a note on one of my favorite images. It's an image drawn by the hand of none other than Galileo. An image showing Jupiter at the center, that wheel-like structure, and 4 dots of light that Galileo observed. And as you all know, when Galileo first spotted these points of light, he thought they were just distant stars, and he named them the stars of Medici. That's because Galileo was no idiot. The Medici family was funding him, and so the right thing to do was name them the stars of Medici so that they would keep the money flowing. But of course, being the diligent astronomer, Galileo noticed in those early months of 1610 that these stars were moving. And through his diligence, he was able to reveal that not only were the stars moving, but they were revolving around Jupiter. And that, of course, was heretical at the time. And that's what led to him being put under house arrest by the Inquisition. But through his careful charting of the moons of Jupiter, Galileo helped put the final nail in the coffin of Aristotelian cosmology, the idea that the Earth is at the center of the universe and everything revolves around the Earth. Galileo opened up the doorway to the Copernican revolution and really helped transform our understanding of physics and how physics applies not just here on Earth, but also to worlds and wonders beyond Earth. And it's my hope that 400 years from now, our descendants will look back at this time in the history of science and exploration as the time in which we made that great leap, we made that great step in exploration to perhaps revolutionize our understanding of biology. Because for the first time in the history of humanity, we can actually go out to these distant worlds like Europa and Enceladus and directly search for signs of living life. And so I hope that this time, this period in which we are living, will be looked back upon as the time in which we did that great exploration and we potentially brought the universe to life. So I'll finish there. And again, if you enjoyed my talk, you can learn much more about all of these worlds in my book. And thank you so much for the invite and your attention. Let's see, I think I can stop sharing here. And I'm happy to entertain any questions.
I think there's one in the chat. I think you answered the first, there's two in the chat. You answered the first one. And why did NASA not prioritize the Europa lander mission?
So I'll try and be both unbiased and unpolitic here. But in my opinion, it's a real shame because we had a unique opportunity. The science portfolio of NASA and the Planetary Science Directorate within NASA is determined largely by these committee reports that are put together roughly once a decade by the National Academies of Sciences. And that report just came out this past summer. And the top priority was to continue with Mars sample return, which is great. And then the next big mission that will be funded in the decade to come is a orbiter and probe to go out to Uranus. And that's great. There's a lot of great science to be done out at Uranus, atmospheres and other stuff to study. It'll help us understand ice giants as a class of planets, perhaps providing some connection to various types of exoplanets that we see. And Uranus has a number of icy moons that are intriguing. But that science is definitively solar system formation, planet formation science. The science which truly excites me is the search for life beyond Earth. And that was not prioritized in that second flagship mission. Enceladus got the third billing, and that's great. I'm excited about Enceladus. But there I would offer a bit of criticism in the way in which the committee went about its assessment of the maturity of various missions and the science potential of the various worlds. You know, the radiation environment of Europa scares away a lot of panels and committees. It does mean that you're going to have challenges associated with the engineering, that you might need to have a shorter lived mission than you would at a more benign environment, perhaps like Enceladus is. But the reality is you may be trading one challenge for another. At Europa, we've got the Clipper mission going out there where we've already invested nearly, by the end of the time, it'll be about $5 billion for the Europa Clipper mission. And so there's a lot of reconnaissance capability that NASA committed to with Europa Clipper, and Europa Lander was going to build on that. We have no such reconnaissance mission heading out to Enceladus. Saturn, which is 10 astronomical units away, requires radioisotope thermonuclear generators, at least a few of them, to power a surface mission. That's got all sorts of complications associated with planetary protection. The Europa lander mission concept, we were battery powered, solar powered carrier stages. You saw Jupiter's close enough that you can use solar power. And so we actually embraced radiation and battery powers in a shorter lived mission from the standpoint of planetary protection. Once that spacecraft is on the surface, we get our science done. The batteries drain over the course of several months. And once that spacecraft is dead, the radiation sterilizes it. And should that spacecraft ever get subducted into the ocean below, it won't pose a contamination risk to the ocean. You can't do the same thing at Enceladus, and especially if you're carrying heat sources such as RTGs, you got a big headache on your shoulders. So I love Enceladus, but I think the Academy made a mistake in that prioritization. Other questions out there?
One in the chat about where the water came from on Europa.
Oh, sure. That's a fantastic question. And in brief, and as Bruce knows, I read about this somewhat extensively in my book. In brief, I'd like to flip the question on its head and say, where did the water come from for Earth? The inner solar system is where the water is not. The inner solar system is where the rocky, dry worlds are in our solar system. I like to think of our solar system as sort of a campfire, and the sun, of course, being the fire. And if you're too close to the sun, you get kind of baked out. And during planet formation of the rocky planets, volatiles, gas species or light molecules, were all kind of baked away from the inner solar system. And eventually they condensed out in the colder regions of our solar system. And so Mercury, Venus, Earth, and Mars, and the asteroids are quite dry. But once you get out to Jupiter at about 5 AU, it's cold enough that ice can form from the gas molecules of water, and you can start to form smaller ice particles that accrete. And so Europa, Enceladus, many of these moons of the outer solar system are where the water is. And it's also where the methane is, the ammonia is, the sulfur is. A lot of the carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, a lot of the elements that you need for life are in great abundance in the outer solar system because of the way the solar system formed and because of the accretion of these different kinds of ices when these moons formed. And another part that I go into in my book is sort of this other Goldilocks scenario where you want to have just the right abundance of light elements like the hydrogen and oxygen that make up water, like the carbon that we think is needed for life. But you also want to have the heavy elements. And so there are certain moons, and Enceladus may be one of these, where perhaps its density is too low, that it does not have that much of a lifetime for water rock interaction. Whereas there are others like Europa, where its density is significantly heavy, so as to indicate that it has a lot of rocky material in the interior. So there's a lot of water out in the outer solar system, as well as a lot of the other material that life needs.
Question.
Sure.
If NASA offered you the chance to go ice fishing on either Europa or Enceladus, and you had to choose one or the other, which world would you want to base your hook on?
I would go to Europa, and part of the reason for that is that as amazing as Enceladus is, we don't know how old Enceladus is, and we don't know how long its ocean has been around. There are some studies of the rings of Saturn and the positions and the evolution of the positions of the mid-sized moons like Enceladus. Some of these studies indicate that perhaps the rings of Saturn and the smaller moons formed via an impact tens of millions or perhaps 100 million years ago. And that kind of makes sense. Rings around a planet are not stable. And so there's long been this problem of Saturn's rings. How do you get them to stick around for billions of years? And there are a few kind of ways that I would argue are a bit special pleading logistically or logically. And perhaps a much easier explanation is that a Kuiper belt object came into the Saturnian system 100 million years ago, crashed into maybe a larger moon, perhaps a sister to Titan, and that led to the formation of the rings and also the formation of moons like Enceladus. If that hypothesis is correct, then it might mean that Enceladus is kind of like a fizzing Alka-Seltzer tablet out there around Saturn, and it's not that old, and its ocean may not be that stable or evolved. Now, life might not, pardon my French, life might not give a damn. Life might still arise on a highly dynamic fizzing ocean. But at Europa, we have good reason to predict that its ocean has been there for 4 billion some odd years. Its ocean is primordial. It's in this stable residence of tidal energy dissipation with Io and Ganymede. And life may need time to arise and evolve. So when it comes to ice fishing, I would put Europa above Enceladus.
Thank you.
I see in the comment section, there's a direct message to me. If life is discovered in Europa, do I think it's going to be carbon-based or silicon-based? I think it'll be carbon-based. And that's part of our sort of hypothesis generation for these moons. We could talk about weird life and life unlike anything that we know of. And perhaps the methane and ethane lakes of Titan have completely weird life. But we can't really formulate a hypothesis based on those conditions. But we can say that on Earth, life arose and is sustained in liquid water environments that have carbon in them. And so our hypothesis for Europa and Enceladus is that we have a sample size of 1 of life on Earth. It's carbon-based, and carbon plus water plus a smattering of other elements and conditions leads to life. So on Europa, yeah, I would put my dollar on carbon-based life.
Dr. Hand, I ask this every time we have a presenter who talks about Europa. Have you seen the movie, The Europa Report?
Actually, if you look carefully, you'll see that I was a consultant on that movie.
No kidding. Wonderful.
And so it was a lot of fun. I do a fair amount of consulting for TV shows. Actually, if any of you watch Foundation, I'm the science consultant on that.
Yeah.
I consulted a bit on the first Avatar, on Thor, and a number of other movies and stuff. But with the Europa Report, normally the movie or TV show is not as precious to me, and so when that team for the Europa Report asked for my help, I said, well, listen, gang, if I sign on to this, I need to know that you're going to really take this advice to heart. I realize that you're doing a fictional thing, and humans going to Europa is not really at least in the near term, in the realm of possibility, et cetera. But they said, yeah, we want to do right by you. So I signed on to it. And they had no idea about the radiation environment. And those of you who have seen it knows that becomes a pretty significant plot element. And they did a really beautiful job of reconstructing the surface. Bear McCreary, who's also of Lord of the Rings music fame. He's doing the Rings of Power score. Bear McCreary did the score for Europa Report, and that movie was made for about $8 million. And they didn't have money to do the vomit comet and the microgravity things or truly extensive CGI stuff. So a neat little fun fact. When they're in microgravity, they're actually in their little spacecraft reconstruction in Brooklyn, New York, and they were lying and rolling on yoga balls to simulate floating around, and they just green screened them out. So pretty clever and a great team to work with. So hope you enjoyed it. I think it's
good movie.
It's held up pretty well, especially when like the $8 million figure for their budget and all that.
Yeah, for anyone who hasn't seen it, it's streaming either on Netflix or Prime right now. You can see it. I forget which service, but when I'm passing through, I see one of them is offering the Europa Report. So I'd suggest you watch it. It's good. It's one of those rare, serious science fiction movies, and it's good.
Yeah, and they got some good actors. One of them is a South African actor who's gone on to a number of other films, the name of which I forget, but
yeah. So watch it. It's good. And the life form you showed didn't look totally unlike what was in the Europa Report.
Yeah, and that so that final animation is from that IMAX that I made with James Cameron, and that was before Avatar came out, and Cameron's vision for Avatar was heavily informed by the dives that we made in 2003 to the hydrothermal vents.
More questions? Anyone? No, I think we're good. That was excellent.
Thank you so much. Thank you.
Thank you so much. A lot of fun chatting with you, and great questions, and keep on looking up at the night sky. Obviously so beautiful, and thank you for hopefully Europa Lander gets support in the future. Who knows, maybe I'll start a private foundation to try and get it done. So keep your eyes out for a Kickstarter.
Thank you.
Take care all.
Thanks. That was great.
Okay. So, Bruce, I'll hit you up again. What's on tap for next month?
Next up, we have a local guy, everybody from JPL. His name's Joe Nielsen. He's from Villanova. For those of you that have been around a while, he spoke to us in 2019. He was part of the team that took shadow image of black hole, and he's completed black hole astrophysics. Okay, so he's going to talk about more recent work that he's done imaging giant black hole in the center of our galaxy, and he's part of the team that's been working on that. They've been processing the data, I think, for like 3 years. So yeah, local flavor should be pretty interesting, and we'll get more from the planetary and astrobiological to very astrophysical.
So you're finally giving us a meeting for us images.
Yeah, right. Kind of feels different. Yeah.
All right. Thank you all for coming tonight, and we're looking forward to that presentation next month because black holes are always fun. And we look forward to seeing anybody who wants to show up because it looks like we're gonna have a great night out at well, I keep wanting to say BBA, but it's Red Clay on mine, it's now. But for our home club field and getting under the stars, shaking out that work here. Thanks again.
Thank you for the feature too.